Mathematical modeling of food processes. Why should we care? This video is part of a course on food physics, of which this belongs to the modeling section. It is the first of a three-part series consisting of rationale, principle, and steps. So first we talk about the rationale. To remind ourselves, our context is modeling of food processes. So there are, of course, many ways to model, and all those different approaches can be broadly grouped into two, physics-based or observation-based, also known as data-driven. Physics-based models follow from fundamental physical laws such as conservation of mass or conservation of energy. They provide insight into the physical processes in a manner that is more precise and more trustable because we start from the universal conservation laws and the parameters are measurable using available techniques. Physics-based models assume that a model is known, meaning we know what the process is. We know the physics. We know we have a qualitative description of the process. This can be difficult for a complex process. Now, of course, a physics-based model can be adjusted based on measured data. In contrast, observation-based models are inferred primarily from the measured data. They are black box models to different degrees in relation to the physics of the process. They're good when time and resources do not permit a complete physics-based understanding of a process. For foods, macro scale models as opposed to micro scale or molecular scale. Here, microscale or molecular scale or mesoscale like Lattice-Boltzmann have been the most numerous and successful. So here, the macro scale modeling, the transport reaction framework is one of the most common physics-based or mechanistic approaches. Before we go into the details, it is nice to look at an example. So let's look at rice puffing and what we learn from a model. Here we see the rice grain and here we see puffed rice. Now below in these videos we see half of a rice grain with a cutaway view, and so as the heating goes on the temperature increases, and as the temperature increases whatever little water there is it evaporates and the pressure increases, as you can see. And then as the pressure increases, it's going to make the rice expand, but then the rice is hard. And the pressure leads to expansion only because at higher temperatures, the material gets soft. So initially it's red, so it's very hard, but it softens. As it softens, then the pressure can make it expand. Now you can see, of course, variation with time, but you can also see variation with space. So you can see this kind of a corner, the end of the rice, it heats the fastest and therefore it expands the first. So you can see in a tiny rice grain, you can see all these very complex processes happening in space and time. Now think of what type of experimentation would you design to get the same understanding? Nothing that I know of. It would be very, very difficult to do this, virtually impossible. But modeling allows us, physics-based modeling allows us to dig into this kind of detailed physics and how it changes in space and time, and therefore gives a very comprehensive understanding of the process. So what are the rationale for doing such mathematical modeling? Rationale number one. Perhaps the most important rationale is that modeling is one of the three pillars of science, along with theory and experimentation. It is not an add-on. Just like experiment and theory, these two are needed. Modeling is needed for more realistic and complex systems with the same purposes of understanding, optimization, and prediction capabilities. Why model rationale number two? It serves critical functions to be able to predict and to understand and optimize. To be able to predict, for example, is critical for food safety, for example. And then understanding and optimization, the applications, the biggest one is in computer-aided food engineering. And that can reduce experimentation, reduce time to market, and so on. Also, building intelligent food processing machines and intelligent techniques like digital twin that are coming up it needs model of the kind we are talking about. Why model rationale number three, which is going to be a long one? Modeling can uniquely enable certain aspects of research, education, and manufacturing. In research, for example, it can show how and why and learn from previous knowledge. Let's look at these in more detail. Modeling is especially useful for more complex systems to keep track of all the different physics and processes that would be going on. As an example of how modeling can help us understand a very complex process, let's look at microwave drying of a cube of potato. So electromagnetics describes how the electromagnetic energy, the microwaves, are absorbed in the cube, and because this is done at 10% power level, which means the microwaves are on 10% of the time and off the rest. That's what is showing here in the cycling. So with the electromagnetic absorption, the temperature rises, and with temperature rising, there is evaporation of water internally inside the cube, and that causes pressure to increase, and as the moisture is lost, so the water transports and the vapor transports out. As the moisture is lost, it shrinks, but it also would be puffing a little because of the pressure. So all of these different physics are going on in position and time. Think of how difficult it would be to try to achieve this level of understanding with experiment alone. You have probably heard of systems approach. Through modeling, we can keep track of all that could be going on in bread baking. So let's see. We have the porosity and the modulus, how soft or hard the bread is, or the color, the final color. That is what we are interested in, but it's a function of energy absorption, heat transfer, evaporation, water transport, vapor transport, shrinkage, swelling, rubbery, glassy, transition of the material, the changes in modulus and changes in color. All of that can be put together in a modeling framework. Such a level of mechanistic understanding of a complex system is difficult to achieve with experimentation alone. No wonder modeling related research work has taken off over the years, as you can see from the publication of of drawing related work over time. Those were some of the examples of modeling used in research. Modeling and simulation can greatly enhance education. It is particularly useful for interdisciplinary training where a model simulator replaces knowledge from one discipline. And let's look at an example. So here is an educational module built around simulation of a canning process. So you can see here simulation can show how the heat is transferred into the interior content and also how the bacterial death occurs and how it changes from surface to the center. So this canning involves food science aspects as well as heat transfer, for which the food scientist may not have all the mathematical details. Conversely, the engineer may know heat transfer but not the microbial aspects of the canning process. Both the food scientist and the engineer, however, can still try different what-if situations by just pressing button here. What if my processing temperature is changed? What if there is a drop in processing temperature? What if my can size changes or the shape changes? These can be tried without getting into the details of both the discipline. Again, all modeling and simulation details are hidden, as you can see here, so the user does not need to be expert in any one of the discipline. Such a simulation environment allows education to be more interdisciplinary while implementing active learning. Yet another example in education. Incorporation of simulation makes it easier to address many pedagogical aspects. Let's look at some. For example, getting across difficult concepts can be helped using simulation or games built upon simulation. Then repeating experiments, doing multiple runs to get data for different conditions in a lab class is often difficult due to the time and resource needs. Experiments can be extended with model simulations, which are also called virtual experiments that you may have heard of. And I have already mentioned to you how interdisciplinary training can be made easier using simulation. I showed you examples of research and teaching use of modeling. Finally, one of the great use of modeling would be in manufacturing. The biggest and the most obvious area for model use in manufacturing is computer-aided engineering that replaces this kind of a prototype-based design where we build and test many to optimize with simulation-based design where we reduce the number of experiments and the number of prototypes. Modeling allows design sensitivity at a reduced cost due to reduced experimentation. Because a model can provide answers quicker, industry can innovate faster with increased efficiency, agility, scalability, and flexibility. Models can help extend one's expertise into another discipline, as shown in the canning example earlier, by having a simulation software that simulates the heat transfer and microbiology. The user can effectively bridge between microbiology and heat transfer. Another rapidly evolving area is machine learning and the building of digital twins. Physics-based models of the kind we have been talking about can take a long time to simulate complex processes. However, once those simulations are done, then that output from that simulation can be used to train neural network and machine learning models, and thus machine learning models can be combined with physics-based models to make faster simulation possibilities that can be used in the real world. To summarize this video, modeling is part of science. It is one of the three legs on which scientific understanding stands. Modeling is an enabler. It allows us to understand complex systems better, leading to better optimization and predictive capabilities. All three possibilities help the three sectors that we know of: industry, research, and extension or education. Industry is helped through computer-aided manufacturing that makes design faster with reduced time to market, research through complex systems understanding, and education through allowing students to be in active learning mode, trying what-if scenarios. So that was all about rationale for modeling. The next two videos in this series will discuss some of the generic principles and generic steps in modeling.